Sure. We've discussed, one of the primary sources of many ODEs in real-life applications is Newton's second law of motion, F equals ma. In this example, we're going to see how an ODE arises from applying Newton's second law. Specifically, we will use our model to determine something known as the terminal velocity of a falling object. We will see that in the presence of air resistance, the velocity of a falling object does not increase indefinitely. There will be a terminal velocity, which is very interesting. So let's dive in and see what our example looks like. It says an 80-kilogram skydiver steps out of an airplane. Assume that one, the only two forces acting on the skydiver are the force due to gravity and the force due to air resistance. Gravity is constant and acts uniformly downward with an acceleration g equals 9.8 meters per second squared. Later, we will see an example in another video. We will see an example where we actually consider the variation of the gravitational force with the distance from the center of the Earth. But for this example, gravity will be equal to mg. M is the mass, g is the acceleration due to gravity. Our next assumption is that the magnitude of the force due to air resistance is proportional to the speed with constant of proportionality k equals 8 kilograms per second. And this force, the force due to air resistance, acts opposite to the direction of the fall, opposite to the direction of the velocity vector. And then our last assumption is that the skydiver leaves the airplane with no initial vertical velocity. So the initial velocity of the skydiver is assumed to be 0. And then the problem asks us to find the skydiver's velocity after 30 seconds. So that is what we want to do. Let me start by making some general comments about the situation described in this example. So we're looking at a falling object and we want to study its motion. In particular, we are interested in the velocity of the falling object. So let me draw what we have. So here is the Earth. And then here is our skydiver. I'm going to draw our skydiver as a ball. This is like a person falling. And we want to study the motion of this skydiver as it's falling. In particular, we are interested in the velocity. And right away, Newton's second law of motion comes to mind when we want to study the motion of an object. And as I mentioned in another video, to apply the Newton's second law, we need to set up a coordinate system and draw a free body diagram. By free body diagram, I mean a diagram where we show all the forces that are applied to the object of interest. The object of interest here will be the skydiver, our skydiver who is falling. So what I'm going to do now is that I'm going to set up a coordinate system, x, y, z. Of course, here the motion will be in one direction, in only one direction. But let me consider an x, y, z coordinate system. I'm gonna choose my y-axis to be perpendicular to the surface of the Earth, and so the motion will be along the y-axis. This is my choice. You can choose your coordinate system different. It doesn't need to be exactly the way I will do it. So here we go. I'm gonna do this as the x-axis, and then we have our y-axis. Positive y-axis is upward, perpendicular to the surface of the Earth, and also we can have a z-axis. But although I drew x-axis, y-axis, and z-axis, here the motion is gonna happen along the y-axis. The fall will be perpendicular to the surface of the Earth. And now, since the motion here is happening in just one direction, we can actually represent the position, velocity, acceleration, and force using signed numbers instead of vectors. That said, I personally prefer to work with vectors. So what I'm going to do is that I'm going to give a name to the position of our skydiver at time t, to the velocity, and to the acceleration. And of course, we have to, in our free body diagram, we have to clearly show the forces that are actually acting on the body as well. So let me first give a name to position, velocity, and the acceleration, and then I will draw the free body diagram, making sure that it's very clear which forces are acting on our skydiver. So here are my names. For the position, I'm gonna use like R of t. This is the position changes in the y direction, so it's gonna be a vector in the direction the of y-axis. So it's gonna be a multiple of j. J is the unit vector in the positive y direction. I'm gonna call the coefficient y of t. Y of t times j. So when the position is only in one dimension, sometimes when people talk about the position of a particle, they just mean y of t, this signed quantity y of t, instead of the vector r of t. Just to be very clear, the j that I wrote here is the unit vector in the positive y direction. So let me be clear about j as well. Here j is the unit vector, vector in the positive y direction. Vector in the positive y direction. That means that j, the vector j, has coordinates 0, 1, 0. That is the vector j, right? What about the velocity? I'm gonna use the letter v for the velocity of our skydiver at time t. V, it's a vector, but here, since the motion is along the y-axis, it will be a multiple of j again. That multiple, I'm gonna use the letter v of t without arrow on top. And again, since the motion is in one direction, many times when we have a motion in one direction, when we talk about velocity, instead of referring to the vector velocity v with arrow on top, we are referring to this coefficient little v of t without arrow on top. Keep that in mind. So velocity can mean two things when you have a motion in one direction, when you have a one-dimensional motion. You may actually, what you mean by it can be this vector quantity, or it can be the little v of t that you see on the right. And then the acceleration a of t, it's a vector, it will be the derivative of the velocity. I'm gonna call the coefficient atj. So please notice that the derivative of r with respect to time is v, the velocity vector v. The derivative of the velocity vector with respect to time is the acceleration vector a of t. So we have these relationships that dy dt is equal to v of t, and dv dt is equal to a of t, right? It is based on the definition of velocity and acceleration. All right, so I introduced the symbols that I'm using to describe the motion. Also, let me do my free body diagram. Remember, every time you want to apply the Newton's second law, set up a coordinate system, make sure the symbols that you're using are very clear, and also draw a free body diagram. Free body diagram means that you look at the object of interest, and then you make sure that all the forces that are applied to that object are clearly drawn in your free body diagram. So what forces do we have here according to the statement of the problem? One of the forces definitely is the gravitational force. I'm gonna denote it by Fg. Fg, that is the gravitational force. And also we have the air resistance force, which is in the opposite direction of motion. Okay, so according to the statement of our problem, we have also the force due to air resistance. So I'm going to call that Fd. All right. So we have our free body diagram. Also, I need to explain exactly what Fg is, what Fd is. Fg we know what the force due to gravity is according to the statement of the problem. We are assuming that the force due to gravity is constant. It will be equal to m times g. Now, since it is pointing in the direction of negative y-axis, that is, it is pointing in the direction of negative j. Negative j. So as a vector, this will be mg times the vector negative j, right? Because it is pointing downward. Negative j is the unit vector in the downward direction along the y-axis in the downward direction. And what about FD? Well, what can I say about the force due to air resistance? Again, according to the statement of the problem, it is proportional to the velocity, but it acts in the opposite direction. The constant of proportionality we denoted by K. So FD is equal to negative K times the velocity vector V. Whatever the direction of the velocity vector is, the direction of the force due to air resistance will be the opposite direction. That is why we have this negative sign. So this is really, really good. I have my free body diagram. I set up my coordinate axis, and also I introduce the symbols that I'm using for position, velocity, and acceleration. I'm using vector notation, but many times when people they're dealing with a motion along one dimension, in one dimension, they only use the signed scalar values instead of the vector representation of these quantities. All right, so now that we have all these, now that we have our coordinate system, we have our free body diagram, the next step is to apply the Newton's second law. So what was the Newton's second law? The total force applied to the body is equal to a mass times acceleration. So the next thing that I'm gonna do, I'm gonna apply the Newton's second law. So I'm gonna write m times a is equal to the total force applied to the body, which is the force due to gravity plus the force due to air resistance. Okay, so far so good. So now I know what Fg is, I know what Fd is, I know what A is. So I'm gonna rewrite this as m a t j, right, equals the force due to gravity is negative mgj. Here we had it here. Right? The negative sign, again, it's indicating that it is pointing in the same direction as negative j, as the vector negative j. And then the force due to air resistance, that is negative kv, but v is vtj. So this is negative k VTJ. Awesome, awesome, awesome. Now, all of these things are in the J direction. Immediately, I can conclude that M times AT is equal to negative mg minus kVT. So this is what Newton's second law is telling me. Let me make a quick comment about what happened here as well. This is something that you will carefully study in a linear algebra course. That if you have two vectors represented in terms of I, j, and k, if you know that ai plus bj plus ck is equal to mi plus nj plus lk, then you can immediately conclude that a must be equal to m, b must be equal to n, and c must be equal to l. This is due to the fact that the vectors I, j, and k, they are linearly independent. Now, I is the unit vector in the x direction, j is the unit vector in the y direction, k is the unit vector in the z direction. And that is actually what I used here. Here, I had a vector. It was on the left-hand side, 0i plus matj plus 0k. And on the right-hand side, I had negative mg minus kvtj, 0I, 0k. And then I noticed that the coefficients of the j vector on the left and the right one must be equal. So mat is equal to negative mg minus kvt. Now, and what do we do next? Remember, the quantity of interest in this example was the velocity of the skydiver. So I'm gonna write this a of t in terms of velocity. I know that a of t is the first derivative of velocity. If I was interested in the position, I would have used the fact that a of t, the acceleration, is the second derivative of the position. But here we are interested in velocity, so I'm going to replace a of t by the first derivative of the velocity. So the next step is that this left-hand side is m dv dt, and the right-hand side, negative mg minus kvt. Now we have a first-order linear differential equation for the velocity of the skydiver. The velocity of the skydiver, and now here by term velocity, I'm referring to this signed quantity v of t. The signed quantity v of t that I introduced here. The velocity of this skydiver, it satisfies this first-order linear differential equation. Now, before attempting to solve this equation, let me rewrite this and clean this up a little bit. Maybe this is actually good the way it is, but let me play a little bit with it. This can be written as, you don't have to do this. At this stage, this is a good enough equation, but if you like, you can rewrite it as follows. This can, as we will see, it can help in solving the equation if we rewrite it. Not necessarily, you don't have to do it, but if you do it, it can help. This can be rewritten as dv dt equals, I'm going to divide both sides by m, negative g minus k over mvt. And also, if you like, you can factor out negative k over a over m, negative k over m, and write this as dv dt is equal to negative k over m times vt, v of t, plus mg over k. Awesome. This is your first order ODE for the quantity v of t. By solving this first order ODE, you will know what v of t is. Of course, this, as you know, when we solve this first order ODE, we will have infinitely many solutions. We have to apply our initial condition in order to select one solution among all the infinitely many solutions of this equation. And we know what the initial condition is. The initial condition is that the velocity at time 0 is 0. When the skydiver left the plane, the statement of the problem told us that the velocity was 0. So let me actually write the initial value problem, the equation, together with the initial condition. Just the purpose of these videos actually were to just come up with the differential equation that describes the phenomenon. At this stage, we have our differential equation, but for this specific example, I want to do more. I want to actually solve the differential equation and fully answer the question that we had in the statement of the problem. So what will be the initial value problem that we are solving here? So the initial value problem, IVP, we need to solve in order to determine the velocity of the skydiver is, we need to solve is dv dt, v of t is our unknown function, equals negative k over m times v of t plus mg over k. Please notice that m is given, k is given. G is known. The only unknown here is V as a function of t, velocity of the skydiver as a function of t. And when you only consider this differential equation, you will have infinitely many solutions for this first order linear differential equation. If you want to pick out one, you need to use your initial condition. The initial condition here was that V of 0 is equal to 0. A skydiver leaves the plane with no initial velocity. So this is our initial value problem. Now, as you know, the standard method that we have for dealing with these initial value problems at this stage is to first focus on the differential equation, find all the solutions to this differential equation. Your solution will have an arbitrary constant, and then impose the initial condition. So first find the general solution to the differential equation, and then impose the initial condition. I'm going to do exactly that in order to solve this problem. So for this example, I'm actually going to solve our differential equation together with the initial condition, which is more than what the purpose of the videos are here. The purpose of the videos are mostly about coming up with the differential equation that describes the phenomenon under consideration. So let's solve this. I'm going to begin with the general solution. That means that ignore the initial condition, just focus on the equation, general solution of our ODE, of the ODE. So the question is that how to solve this equation. dv dt equals negative k over m v of t plus mg over k. My friends, one way to solve this is to identify this as a first order linear equation. And then you can follow the steps that we have for solving a first order linear equation to find the solution, finding the integrating factor, and so on and so forth. So that is one way to solve this equation, which is perfectly fine. You can do that. But for this example, there is a shortcut. So let me first write that you can obviously solve this problem by following the steps that we have for solving a first order linear equation. You can solve this using the steps we have for first order linear ordinary differential equations. So that is one way to solve this. However, here there is a shortcut. Let me tell you what the shortcut is. Alternatively, you may do something clever. You may let w of t, introduce a new variable w of t as v of t plus the constant mg over k. This guy that appears here. Call this w of t. Now, notice that this mg over k is a constant number. This mg over k is a constant number. So clearly, the derivative of w with respect to t is exactly the same as the derivative of v with respect to t, because mg over k is a constant number. So we can rewrite our equation as, we can rewrite the ODE as follows. The ODE of interest as follows. On the left-hand side, I will have dw dt, because dw dt is exactly the same as dv dt. And then on the right-hand side, I will have negative k over m and multiplied by w itself. So the equation that we want to solve, the left-hand side dw dt, the right-hand side negative k over m, which is a constant number, times w. And there is one ODE that anyone who wants to claim that they know ODEs, they need to memorize the solution to. And it is the ODE of this form. when you have the rate of change equals a constant number times the current value. If you have du dt equals some number alpha times u, right? This ODE, you can again solve it as a linear equation or solve it as a separable equation, but it's a good idea to memorize the solution to this ODE. This is one of the basic foundational ODEs that we need to be familiar with. The solution is exponential. You can immediately say u of t is equal to a constant, arbitrary constant, times e to the power of alpha t. Alpha is the number that is appearing, the constant number that is appearing as the coefficient. So knowing this basic fact, you can immediately say that W of t here is C times e to the power of negative k over mt. So this is our shortcut. Our shortcut was based on knowing a very fundamental basic fact about those equations where the rate of change is proportional to the current value. When that happens, you know exactly what the solution is. So here we use this basic fact. Now that I know W of t, that tells me that because W of t, remember, it's V of t plus mg over k. That is W of t. So this is c e to the power of negative k over mt. And so immediately I can conclude that V of t, the velocity that I was interested in, is negative mg over k plus c e to the power of negative k over mt. And of course, at this stage, c is an arbitrary constant. How can I find c? I will impose my initial condition. Impose the initial condition. That is how we usually solve our initial value problems, right? First, we find the general solution of the ODE, and then we impose the initial conditions. So here, what was the initial condition? V at 0 is equal to 0. A skydiver leaves the plane with no initial velocity. What is V at 0? Look at our formula for V. This is V at t. So what will be V at 0? V at 0, every time I see t, I have to replace it with 0. Negative mg over k plus c times e to the negative k over m times 0. That is V at 0. And this must be equal to 0, right? The left-hand side must be equal to the right-hand side. So what does this tell me? So negative mg over k plus c, because e to the power of 0 is 1. This is equal to 0. That tells me that c, the constant that I was looking for, is mg over k. Now that I know c, let me call this 1. And then I'm going to call this 2. 1 and 2 together tell me exactly what the velocity of the skydiver is as a function of time. 1 and 2, they tell me that V of t, the velocity of the skydiver at time t, is equal to negative mg over k plus c is mg over k, times e to the power of negative k over mt. If you like, you can factor out mg over k and write this as V of t is equal to mg over k times negative 1 plus e to the power of negative k over mt. Beautiful. Now we can compute the velocity of this skydiver at any t. The statement of the problem says that compute the velocity after 30 seconds. So I'm going to do that. As a consequence of this, we have after 30 seconds, I have to compute V at 30. T equals 0 is when the skydiver leaves the plane. After 30 seconds, T is equal to 30, equals M. The mass of the skydiver, the student of the problem says that mass is 80 kilograms. G, the acceleration due to gravity, that is 9.8. This was also given to us. This is a known constant. It was also given to us in the statement of the problem. So here the units where the mass 80 kilograms and 9.8 is meters per second squared. We are using SI units here, if you're familiar with SI units. And then K, it was given to us, is 8 kilogram per second. And then we have -1 plus e to the power of -8 over 80, and then t is 30 after 30 seconds. I want to know what happens after 30 seconds. So what we will have here, 80 over 8 is 10. 10 times 9.8 is 98, so that was easy. And then we have -1. What we have in the exponent here, 30 and in the numerator, 80 in the denominator, the tens cancel. 8 and 8 also cancel. We will get -3. We will get -3. So it will be plus e to the power of -3. Now, if you like, you can use your calculator at this point. This is approximately -93.1 meters per second. That will be the velocity of the skydiver after 30 seconds as a signed number. If you want to write it as a vector, you can write the velocity after 30 seconds. The vector velocity is -93.1 times j. 93.1 is the magnitude, and it's in the direction of -j. It's pointing downward. Now, there is one more thing that I answered the question that was asked in the statement of the problem, but there is one more point that I want to make here. Look at our formula for the velocity. Here it is. This is the velocity after t seconds, the velocity of the skydiver after t seconds. I want you to notice that as t gets bigger and bigger, this quantity, e to the -k over mt, goes to 0, because -k over m is a negative number, and e to the -k over t, as t gets bigger and bigger, it gets closer and closer to 0. So this is an extra observation that I want us to make here. This was not part of the question, but let's make this observation. Observation. Note that, as a matter of fact, this is true regardless of the initial velocity. Even if we use this formula, where we have this c there, where we have not imposed the initial velocity yet, still this term, the second term, goes to 0. Note that, so let me write it here. Limit, note that, regardless, let me be clear about this, regardless of the initial velocity of the skydiver, velocity, limit as t goes to infinity of v of t is equal to limit as t goes to infinity of -mg over k plus c e to the -k over mt. And this second term, as t goes to infinity, goes to 0. So this is just -mg over k plus 0, which is equal to -mg over k. So what this is telling me is that as time increases, this v of t, the velocity, tends to this number. It will not increase indefinitely. It will not grow without bound. And maybe the intuition tells us that as time passes by, the velocity increases, gets bigger and bigger. But what we see here is that when we consider air resistance, when we consider the force due to air resistance, there is a terminal value for the velocity. This is what we call the terminal velocity. So let me also write this. That is, as t gets bigger and bigger, as t approaches infinity, v of t tends to the terminal velocity, -mg over k, j. Very interesting. Now, if you like, in our example, where the initial velocity was 0, in our example, negative mg over k is equal to negative 80 times 9.8 divided by 8, which is negative 98 meters per second. This is the terminal velocity. If you actually draw the graph of v of t, so let me actually attempt graphing this velocity profile. So here we go. This is t. This is, let me give myself more space here. The axis v of t upward. Of course, our v is negative v of t. Okay. And remember what was the formula for v of t in our example? V of t was equal to negative mg over k, which is in our case, negative mg over k is negative 98, and then we had negative 1 plus e to the power of negative k over m, negative 8 over 80 times t, right? This was the function representing the velocity of our skydiver. You can use MATLAB, or you can play with it a little bit. If you graph this function, and this is the profile that you will see. It will look like this. Let me have negative 98 here. This will be like a horizontal asymptote. Your graph will look like this. So this 98, negative 98 is our terminal velocity. This is an interesting situation. So when you consider air resistance, there will be a terminal velocity. Of course, without air resistance, the velocity would increase indefinitely. There will be no terminal velocity. We also notice that after 30 seconds, as a matter of fact, we are very close to this terminal velocity. Just after 30 seconds, we are very close to this terminal velocity. After 30 seconds, the velocity is negative 93. So maybe I put 10 seconds, 20 seconds, 30 seconds. After 30 seconds, we are close to this negative 98. All right, excellent. We're done with this example. And I think the beauty of what happened here is that we arrived at a differential equation. By solving that differential equation, we were able to determine the velocity of the skydiver as a function of time. And also we noticed that there is a limit. Like this velocity would not increase indefinitely because of the presence of air resistance.